Welcome you all. In this session, we are going to discuss about the output equation for three-phase transformer. So as I told already, the output equation is one which relates the rated KVA output of transformer to the area of core and window. We call this the output equation. In transformer, the KVA rating depends on two parameters. One is the flux density and the second one the ampere turns. And thereby the flux density is depends on the core area, whereas the ampere turns depends on the window area. The cross section has three limbs and two windows. Each limb carries low and high voltage of each phase. So here you can see the cross-sectional view of a three-phase transformer. As I told, always the low voltage winding will be nearer to the core, whereas the high voltage winding will be away from the core. In order to minimize the insulation, it has been arranged such a way. And one more, WW represents the window width, HW represents the height of window. So now let us derive the output equation of three-phase transformer. So the induced EMF of transformer is given by E is equal to 4.44 F5mt, and the EMF per turn means you are supposed to divide it by T, number of turns. Here the number of turns is denoted by T, so while I am dividing it, I will be getting a value which is equal to 4.44 F5m. The T get cancels. So the window space factor KW is the ratio of conductor area of window divided by total area. So KW is equal to AC by AW. From this expression, conductor area AC is equal to KW into AW. Just I have rearranged the above equation. So the current density for both the windings are same. So the current density is nothing but current by area. So here if I am going to calculate the primary current, then it is primary current by primary area. If I am calculating the current density for secondary, then it is secondary current divided by secondary area. As I told, here both the current density are equal, so I'm just equating it with del. Del is nothing but current density, which is equal to IP by AP, which is again equal to IS by AS. Area of cross sectional of primary conductor AP is equal to IP by del. Just from the above previous equation, just I have rearranged in order to get the value of AP and AS. So now if we neglect the magnetizing MMF, the primary ampere turns is equal to secondary ampere turns. Just you can equate both the ampere turns. AT is equal to IP into TP, which is equal to IS into TS. Primary current into primary number of turns, which is equal to secondary current into secondary number of turns. The copper area AC is equal to twice. So this is in this step you should be careful, because for the single phase it won't be twice, it will be a single one time, but for three phase it is twice the number of primary turns into area of cross sectional area of primary, plus 2 times the number of secondary into the cross sectional area of secondary. So this is the only change we have. So AC is equal to 480 by del, there it is 280 by del. That is the major difference between deriving the single output equation for single phase and three phase transformer. So on equating both the above equations, AW KW is equal to 480 by del, and from this AT is equal to 1 by 4 KW AW, and the KVA rating of three phase transformer is 3 times Vp Ip into 10 to the power minus 3. On substituting, you will be getting a value that Q is equal to 3.33 F 5m kW AW del into 10 to the power minus 3. So the above equation we call it as the output equation of transformer. So here this equation, the KVA rating is expressed in terms of the main dimensions of transformer, the main dimensions KW AW. So we call them as the output equation. So the output equation of single phase is 2.22 F phi m kW AW del into 10 to the power minus 3, whereas the output equation for three phase transformer is Q is equal to 3.33 F phi m kW AW del into 10 to the power minus 3. Thank you.